Now, today's session is on sequencing problem. We'll be discussing case 2, paints n jobs through 3 machines. We had discussed in our last session, case 1, that was n jobs through 2 machines. That means we have made the situation a little more complex. Now, the decision making will be a little more complex because we have 3 different resources. We have taken a practical example. The example says, provide the optimal job sequence involving 3 machines, M1, M2, and M3. The details of time requirement for each job on various machines are given below. So the table shows the time requirement of different jobs on different machines. So J1 spends 7 hours on machine M1. J1 spends 8 hours on M2 and 11 hours on M3. Likewise, J2, J3, J4, and J5 all have their specific time requirements on different machines. Now, another information has been given as the order of machine. That means a job has to start processing from M1. It should go to M2 and then finally it should finish with M3. Now recall in our case 1, where we had only 2 machines, the solution has been given by Johnson and Bellman algorithm. But this is the limitation of Johnson and Bellman algorithm, that can be operated only in case of 2 machines. Now, when you have 3 or more machines, you cannot directly apply Johnson and Bellman algorithm. So, you can convert the problem into that form. Before converting, you need to go for some condition check. So step one is basically for condition check. Condition check. We'll check 2 conditions. Condition 1. Check minimum of M1, which is 7, 12, 11, 9, 8, so 7. Then maximum of M2. So maximum 8, 9, 5, 6, 7. So it's 9. Since minimum of M1 neither greater nor equal to maximum of M2. Therefore condition fails. That means if condition has to be satisfied, then minimum of M1 should be either greater than or equal to maximum of M2. In our case, it is not neither greater nor equal. Therefore, we said condition fails. Let us go for condition 2. So condition 2 talks about minimum of M3. So minimum of M3 is 3. Again, maximum of M2 equals to 9. We have already calculated. Since minimum of M3 neither greater nor equal to maximum of M2. Therefore, condition fails. Now see, minimum of M3 was 3, maximum was M2 was 9. So minimum of M3 neither greater nor equal to M2. So again the condition failed. If both the condition fail, then it is a case of technique fails and you cannot apply Johnson and Bellman algorithm on this. So if both the condition fails, you have to simply write, since both the condition failed, therefore it is a case of technique fails and problem cannot be further solved, right? I hope you understood. So you have to check two conditions in case of three machines. Condition one, minimum of M1 should be greater than or equal to maximum of M2. If that satisfies, then take that. Otherwise, minimum of M3, maximum of M2. Minimum of M3 should be greater than or equal to maximum of M2. Either of the condition has to be satisfied to apply Johnson and Bellman algorithm. If it doesn't, then write technique fails. Fine. Now we'll move to another problem where we will not find technique fails. So this is what our problem is. A machine operator has to perform three operations: composing, denoted by capital C, printing, denoted by capital P, and binding, denoted by capital B, on a number of different jobs. The time required to perform these operations for each job is known as. So see in the table it has been given J1 to J6. There are 6 jobs which passes through C, P and B, and different time requirements for each machine has been given. We are supposed to determine the order in which these jobs are to be processed, also the elapsed and idle time. So we have again two order of jobs. The first this thing, and second elapsed and idle time. Another information has been given like job should be processed in the order of C, P and B. That means job has to start with C, should go to P and finish with B. Now we know when there are three machines, we need to go for step 1, which is condition check. So check your conditions. Here minimum of M1 equals to, minimum of M1 is 3, maximum of M2 equals to maximum is 8. Now since minimum of M1 neither greater nor equal to maximum of M2, therefore condition fails. So this was our condition 1. Let us come to condition 2. Condition 2, minimum of M3 equals to, let me not take M1, M2, M3, it is C, it is P, here also it is not M1, it is C, and this is not M2, it is P. Here it is not M3, it is B. So minimum of B is 8 and maximum of P equals to 8, right? Since minimum of B equals to maximum of P, therefore condition satisfies, right? When one of the condition is satisfied, you can move to step 2. Step 2. So Now we are writing two different variables. First is M2. M2 will be equals to C plus P, and M2 will be equals to P plus B. And we will write we will write a new table. We will write a new table with the help of this algorithm. Fine. So let me copy this. Let me paste here. Let me take out one. This delete. Let this is be M1. This is be M2. Let me delete all this. So what we need to do is, see, we have written M1 equals to C plus B. So for all the jobs, what you need to do is you need to add C plus B, that is 3 plus 8, 11, and write here. For J2, it is 12 plus 6, so it is 18. For J3, it is 5 plus 4, so it is 9. For J4, it is 2 plus 6, so it is 8. Likewise, for J5, 9 plus 3, 12. For J6, 11 plus 1, 12. Next, M2 we have defined as P plus B. So P plus B. For J1, it is 8 plus 13, 21. J2, 6 plus 14, 20. J3, 4 plus 9, 13. J4, 6 plus 12, 18. J5, 3 plus 8, 11. J6, 1 plus 13, 14. Now see, we have converted into the form of n jobs and 2 machines, and now you can apply Johnson-Bellman algorithm. Fine. So now step 3. What was our step 3? That we have to count how many jobs, 1, 2, 3, 4, 5, 6. So we are actually looking for optimum sequence of jobs. What we did in our last problem, we used to take a column matrix 1 2 3 4 5 6, right? Reduce the size, make it at center, and make this thing also as center. So we know if we find least value on M1, we'll enter from top. If we find least value at M2, we'll enter from bottom. So try to look out for the least number. The least number is 8. It is for J4 and it is for M1. So J4 will enter from the top, and we need to cancel J4. So cancel J4. So J4 is no more in the system. Now the next small value is 9. So go for 9, right? 9 is for J3 and 9 is for M1. So enter J3 from the top and eliminate J3 from the system, right? Now the next value is 11 and 21, right? 11 is from top and this is from 11 is for M1 and this is for M2. Now you can arbitrarily choose any of the sequence, right? But since J1 is coming, J1 comes first, right? Before J5, J1 comes. Therefore, we are taking J1, and J1 11 is for M1, so it is entering from the top. So we are writing here J1. Now we will be striking out, we will be striking out J1 from the system. Next is J5, but it is for M2. So the entry will take place from the bottom, J5, right? And cancel J5 from the system. Now, the least value is 12, which is for J6 and for M1. So J6 will be from the top, right? And cancel J6. The left out is J2. So enter J2 here. So finally, we have our optimum solution. Now cancel J2. Now there is no more job in the system. So next is what? Next is our step 4, which is time calculation. Now remember, this M1, M2 are the intermediate one, which was not in the problem, in the original problem. We had derived M1, M2, right? Just to reach the optimum sequence of jobs. Now we do not require M1, M2 as it was not part of our original problem. So our original problem was this, right? This was our original problem. I'm just bringing it down here so that we can apply. Now see, we need to draw a table. So how many number of columns we will have? One column for jobs, then one for C, one for P, one for B, that means 4 for idle time, right? C will be split up into 2, start and finish. P will be split up into 2, start and finish. B will split it up into 2, start and finish. And idle time will be split up